Okay. All right, let's talk about the final. Yay, final, it's finally here. Just a general review in case of people who don't know. It's Tuesday, 8 a.m. here in Brevard. It will last until 11 a.m. and then we're done. SDS students will be contacted over the weekend concerning where to meet. I'll talk to you about it then. Usual stuff, you're allowed to bring pens, pencils, erasers. If you want to bring a ruler, that's great. Highlighters, all that stuff. No notes, no book, no notebooks, no anything like that. I'll provide paper, the test, all that stuff. Bring a calculator. In the test, just going over previous tests, there's things that I've been reminded of. There will be 50 multiple choice, 2 appetizers, and 6 problems. And actually, we can think about this right now. These 2 appetizers will be 5 points each for a total of 10. 6 15 pointers, so that's 90, and then 50 multiple choice, which will be 100, or a total of 200 points. This 200 points will represent 30% of your total grade, and I've shown before how to add all that stuff up. There are some things that I consider to be critical subject material that will be problems on the test, the first of which being vector addition. E-field and or force. There will also be a compound lens. There will also be a circuit analysis problem. There will also be a magnetic induction.
So are these problems given, like, for sure?
I would say that the subject is given for sure. The specific problem will not be given now, but you can pretty much narrow it down to what it will be. Since we did the bar during and a lot of this stuff, it just makes sense. I said we did mirror lens during the test, so that means we got to do compound during the final. We did the bar during the test for magnetic induction. Now we will do the circle for magnetic induction.
So whatever wasn't on our test this semester.
Yeah, now we did cover vector addition, but we're going to do that. So that leaves 2 problems and 2 appetizers that will come from all sorts of different material. Probably B-field addition is a good topic. Potential addition. I haven't written the final. The final will be written over the weekend. One of the things that may be on the table, I haven't decided specifically. I thought, first let's get this number out, and this may be the thing that determines what is and isn't on the test. The test 3 average was an 85.5. That means that no curve is available for test 3. 2-point curve available for test 1 minimum, 0-point minimum for test 2, 0 maximum for test 3, and yet to be determined for the final. So test 3 went really well. It was the easiest of all the 3 tests, I think. One of the problems that people were having were identifying the qualities of an image and drawing it appropriately for a virtual versus a real. Like some people were, and this may be one of the things that I'll have to work in, if you've got a lens, real is on the right, virtual is on the left, and really it's the same side as the object. But for a mirror, virtual is on the right, and real is on the left, on the same side as the object. And so people were getting that messed up a lot. So a lot of these things, I was really looking to see if you knew what you were doing. And there was a large contingent that just kind of fumbled with it. I like to look at what you do well on the test and kind of avoid it on the final. I mean, you guys did the right-hand rule really well, so there's no need to do that. But the application of the right-hand rule game in terms of charged particle motion, that is going to be on the test. Because we need to understand, there's a lot of 3D visualization in this course, and I want to test on it before you guys leave. Let me take a look at the file. Oh, let's see. Particle spectrometer. Let's see, I'm just looking at the particle circular motion.
Is particle circular motion like the appetizer that we did yesterday?
Yeah, like that. Particle spectrometer is a circular motion, except that it's just a semicircle. Single double slit. Thin films. I mean, in some sense, when I saw the average, I thought that the average was way too high for how I was grading, because there was a lot of issues with the lens, and then the initial problem with the light. There were a lot of people messing up the thin film and the single double slit, so stuff like that may come again. I haven't decided. The problem is, and it's a good thing on your part, I am limited to a 3-hour final, which means that I can only cover so many materials. So there may be, most likely, a subject that I don't cover on the final. It most likely will be in the multiple choice, but as a problem, probably not. I don't know what will be excluded yet. Let's see, I'm thinking... Oh, another thing over here, like RC circuits, C construction, capacitor construction, particle motion, in a capacitor, namely the one that is problem 5 from that one test, this one, which we covered on Thursday. And so that's a lot of it. Now, one thing that I will be looking for that's critical are know your units, know your magnitudes, You use ohms for current. I will swing the red pin heavily. And understand that this is the last time that we get to spend some quality time together. And I think that I'll make one last push for you understanding what the alphabet soup method is. I also believe in the 3 forms of numbers, and I'll probably, you give me enough time, I can do some interesting things. You'll be given numbers that you need. You'll be given numbers that you don't need, and I just want to see if you try to squeeze it into the equation. And then other times I won't give you numbers because you don't need them. So there will likely be a substitution problem where you don't have the information. And what the thing about substitution is it really gives the plug and chuggers fits. Because if I don't give you a number for an equation that you have to use, they just go nuts. And so it's my last chance to just pour salt in that wound and then just rub it real hard. So it's the last chance. Also, equation 2 unknown will be gone over. So you will have one last opportunity to die a little more inside. Let's see. Probably small angle approximation. And of course, just your basic knowledge on trig. I mean, nothing fancy. Find it difficult how I could do, but once again, make sure that you still know your basic geometric shapes for cylinder, sphere, all that stuff. I'm not sure what we would do with it, but never hurts. So that's kind of a general overview of the final. There you go. And what we're going to do from now on is just go over problems, and if there are things that I'd want to talk about, I'll talk about it then. So I open the floor for questions. In the back, yes?
Can you do a B-field addition problem?
Okay. What we will do is, actually, I know exactly the one that we'll do. Oh no, I didn't bring it. Okay. So current starts here, and it goes down and around and in and around some more. So there are 3 circles. And you can visually tell that there are 3 hunks of arc. You don't have to worry about the connecting wire. The current is 50 milliamps. I want to know what is the B field at the center. And so a lot of people just go nuts. The first time that I gave this problem in a test, they just freaked out, said it was impossible. The thing that you have to remember is that the B field for an arc is mu naught I over 4 pi r, and it's mu naught I theta. Mu naught, and this constant will be given, is 4 pi times 10 to the negative 7th.
Try to focus the screen.
Yeah. Okay. There will be 3 contributions from the B field. Now, if you do the wrap rule, the current here, put your thumb in the direction, and then what you notice is you claw into the page. The arc A part is going to be negative because the fingers claw into the page. And actually, I've made it really easy. In all of these, they all claw into the page. And because of this, what I'm going to do on this last one, I'll delete it like that, and then I'll make it like this. I'll change its direction. Because if it's going in a counterclockwise direction, the B field coming out is positive. So the total is the sum of those three. Now, in this, what I'm going to do for simplicity purposes is that each of these circles is 5 centimeters. So it's 5 centimeters to the first ring, 10 to the second, and 15 to the third. Mm-hmm.
So basically in these, you're just figuring out if you're clawing in or out and putting a negative in front of either if it's an arc or whatever.
Yeah, if you claw in, negative. If you claw out, positive. So it's negative mu naught I over 4 pi r, and I'm going to go theta 1 and r1, minus mu naught I, or actually to be consistent, theta A, theta B, and theta C.
Could you possibly label, like, you see where you put A, like if you put B where B is and C where C is on the drawing?
Okay, all right, hold on. Actually, I'll just use the same page. Let's take a look at that. So there are 3 arcs. I've removed the connecting wire just to clear things up. You have the outermost wire A, which is 180 degrees. It goes around clockwise, so the B field contribution will be into the page or negative. B continues this clockwise motion for 3/4 of a circle, or 270 degrees. Its B field contribution is also negative. C is counterclockwise for 1/4 of a circle, or 90 degrees, and its B field will be coming out. Now, when you put these values into the equation, and actually I'm going to do one simple thing. I'm going to have a mu naught I out of 4 pi, which leaves this, just so that I can simplify the equation. This gives you 4 pi 10 negative 7. I is 50 milliamps times 10 to the negative 3. This is 4 pi. And then negative theta A minus pi over RA, which is 0.15. Each of the rings is 5 centimeters beyond the other, so the third ring is a total of 15. Minus, the second one is 3/2 pi. And RB is 0.1 meter. The last one, positive, C is 1/4 or pi over 2. And its distance is 0.05. And so that is that. And then you could cross that out, and then now it's just plugging and chugging. So something like this, as simple as this would be a decent appetizer. If I gave you the B field and I set some other conditions, then you would just have to determine what you don't know and continue with the problem.
You can't use like 180 degrees, that it wouldn't work if you used it.
Not numerically. Numerically, the thing would just blow up.
Okay.
Remember when, and this is one of those things where if an arc B field is mu naught I theta over 4 pi r, notice how a circle of B is mu naught I over 2r. And many people have asked, well, where did the other 2 go? Where did the pi go? Well, if theta is a circle, that's 2 pi. That cancels it. So the theta that you use must be in terms of radians. One of the things that could come out, just thinking about it, is I'll give you the arcs and I'll give it to you in degrees and just see who's paying attention and who's not, and watch and see if people dump in 180 degrees when they should be putting in just pi. And so that's a good way to determine if people understand how to use the equation. Yes?
For your R value, why are you multiplying B and C by 2?
Why am I multiplying B and C by 2?
It's asking the 2 on the.
Okay. Good question. 180 degrees, the value of theta is pi. But what I did here is that B is 270 degrees, or 3 pi over 2. 3 pi over 2. So this is relating to the theta. The 0.1 relates to the R. In the last one, C, that's pi over 2. So I simply kept, I used the fraction and put pi over 2 within it. So that's where it came from. Yes?
If you gave us a problem like this, would you keep it to pretty standard like radian degree conversions, or would
Yeah,
you,
I wouldn't use,
like 46 degrees?
no,
Okay.
no. Everything probably would be kept in multiples, at worst 10. Most likely 30, 45, 60, and 90. Stuff like that. Part of me says, oh, why not? Other part says, no, we got other stuff to do. So, yes, any other questions? Did that answer where did the 2 come from? I answered it, okay. Yes.
Can we do a 2 equation, 2 unknown, like how you would do it with one of these problems?
I don't know. Well, the best one for 2 equation 2 unknown is Kirchhoff's law.
But we're not doing, right?
I haven't ruled it out. I just said low priority. It could be.
So you pretty much think the circuit problem is going to be like a circuit analysis. It's not going to be like a Kirchhoff. It's going to be like a circuit analysis.
It's going to be a circuit analysis. That's the thing. I'm killing time. Well, good question. I'll answer it. It's the circuit that. This wasn't specific. This isn't the one exactly like the one from the test, but it illustrates the point. This one over here. And there was a high failure rate for students in being able to solve for the potential at that point. And the now granted, there was I wouldn't say that the class aced Kirchhoff's law. So that's why I'm still kind of wavy. I may put it in, but that's only if I've got a full problem sitting there that's I haven't decided what to do, and I'll just throw Kirchhoff's law in it. Yes, in the back.
Are we ready to like do another one? Or are you ready?
In a little bit, or about 30 seconds. So be able to calculate the potential anywhere within that circuit. Most likely it will be a point within a subset of that circuit. And that's what I mean by circuit analysis. You've got to determine REQ first, then you've got to determine the I0, the current going through the battery.
So like that one.
Yes.
Cool.
All right, in the back, what's your question?
Can we do magnetic induction?
Magnetic induction, okay. And your question?
Just really quick, what test is this on?
This is, it's the spring, yeah. Yeah, all of these are clipped, but it's one of the 2 finals in the Blackboard. All right, what we're going to do is number 6. Given the circle shown below, what is the magnitude and direction of the change in B field? Will it reach 0 or 2 Tesla? How long will this take? The induced current is clockwise, which means that the induced magnetism or the induced flux is into the page. It has to be into the page because it's opposite of the change in B field or the change in flux. So the external has to be out. Since the area of the object is not changing, the dB dt must be out as well. The electromotive force, in terms of magnitude, is d phi b dt. This is simplified to a dB dt. And current, which is electromotive force divided by resistance, is A over R dB dt. Now the dB dt is coming out of the page. So it will reach 2 Tesla. It will not go to 0. Because the B field is out of the page, the change in B field is out of the page, So it will go from 0.4, 0.8, 1.2, 1.6, and then 2. So dB dt is IR over A. This big R is the resistance. Area is pi little r squared. So this becomes I 0.1. The resistance is 2. And then pi little r is also 0.1. So this becomes 20 over pi. And that is 6.37 Tesla per second. Now to answer the final question, at what time will it reach 2 Tesla? You can rewrite kind of like the position equation. B equals B naught plus T dB dt. This means you have 0.4, or actually what I'm going to do, B minus B naught is equal to T dB dt, or B minus B naught over dB dt. I'm kind of treating dB dt as just one value, and that, yes.
Was resistance given?
Yes, 0. No, it was 2. So R was given 2. So final B is 2, initial B 0.4, dB dt 6.37. And I get 0.25 seconds. And so that is the answer for that. Yes?
Could you possibly go in a little bit more detail on how you figure out if it's going into the page or out of the page? Like the very initial
Okay.
start bit?
So if we're looking at these hoops from above and at the side, in this particular case, the B field can do one of two things. It could either change into the page or dB dt out of. Lenz's law says that the induced must be opposite of that change. So the induced, in this case, is out of page. In this case, it is into page. So they are opposite of each other, because what the induced current is trying to do is oppose the external so that the net is 0. in the end, it always fails, but can't help it to not try. I mean, it's got to try. So that lets you know what direction this stuff goes. We're not going to have a bar problem, so it's kind of not a waste in time. I mean, it's helpful, but in terms of what's going on in a circle problem like this, I mean, this is all you need. Now, the one thing that you will need to know is that in the event of the induced flux coming out of the board, that means the current must be counterclockwise. In the event of induced flux going into the board, the B field must, or the current must be in a clockwise direction.
If you gave us the starting B
Mhm.
and the ending and the time, do you still just like move the equation around to find dB dt
Yeah.
for the tune?
Well, if I gave you the initial, yeah, that would be a good question. If I gave you the initial, the final, and the time, you could calculate the dB dt, and then from that. So in some sense, that's a potential problem. So there's only so many ways I can do this, so I have to add some little twist. So that answers the question?
I think so.
Okay.
So the DVDT is the external
Yes,
flux, and then the other one is the induced.
the induced,
Where
yes.
it's got the weird like eye circle.
Yeah, in this particular case, it's the darker vectors, which are the external, and the red, which are the induced. And the current is based on the induced.
Okay.
Is the induced what you usually give us,
No, usually I give you the external.
the DVDT?
But most likely what will happen is I'll give you a different something else.
What color did you say red was?
Red is induced, blue in this case is external.
So like on the problem you gave us on the test, if we look at the current, because you said,
Yeah, if I gave you the current, yes.
okay, because like you drew it on here, so that's what I was saying,
Mhm.
you could see.
Yes. Yeah, because I gave you the direction of the current, it was not needed to be determined. It was just, I mean, it was just it.
Did you ever give us a circuit that had like resistors and capacitors in it?
That would be an RC circuit.
Can we do one of those?
Okay. You have a 10 nanofarad capacitor. It discharges. This is 100 volts. This is 30 volts. The time that it takes to go from 100 to 30 is 8 seconds. What is the value of R? So this would be a decent appetizer. The thing that you could do is let's see, V equals V naught e to the negative t over tau. V over V naught is e to the negative t over tau. Natural log of V over V naught is negative t over tau. That means that natural log of V over V naught is negative T over RC. I need to solve for R, so R is negative T over C, natural log V over V naught. That means that T is 8, C is 10 times 10 to the negative 9th, natural log of 30 divided by 100. And that gives you .64 times 10 to the 8th ohms, or 664 mega ohms. Something else that you could do with the capacitor is, this is a combination of almost like circuit analysis and you have all these resistors here are 1 mega ohm, and then you put a voltmeter in it, and then it's got, let's do a 10 nanofarad resistor. If the voltmeter is non-ideal when tau is 4 seconds, what is the resistance of the voltmeter? So in this particular case, you treat this as a resistor, so it's 1 over 2 times 10 to the 6th plus 1 over 1 times 10 to the 6th plus 1 over R voltmeter inverted, and that is R equivalent.
Wait, what did you say all of the resistors were?
I said all the resistors were 1 mega ohm. And I'm just stabbing in the dark for numbers, so the numbers may have to change slightly just to get it to work, but for right now it is what it is. You know that the time constant is R times C, so REQ is tau divided by C, so REQ is 4 divided by 10 times 10 to the negative 9, which makes it 4 times 10 to the 8th ohms. If that's the case, this may not work, but trying to think. Let me change it back into this. I need to solve for the resistance of the voltmeter. So 1 over 2R plus 1 over R plus 1 over R voltmeter is equal to 1 over REQ. I'm going to move these two over. 1 over R voltmeter, 1 over REQ minus 1 over R minus 1 over 2R. I just changed the order of this. It doesn't really matter. So RV is this. 1 over 4 times 10 to the negative 8 minus 1 over, oh, this is going to end up in negative territory. I'm going to make these 200 mega ohm instead of 1 mega ohm. And that's a plus. Is it still not gonna? Okay, no, I think this should work.
So is the right side not a thing anymore?
What do you mean the right side is not a
Like
thing?
this?
Oh, I'm still using it. The reason why, this isn't.
Okay.
Because the values changed. I'm rewriting this as this. Or changing the values in this.
So do we not look at the right side?
You do look at this. Ignore this. This is useful because you're determining REQ. So you do need this. And then you set up the equivalent resistance circuit for this. Oh, and I still got a bad answer. And so the answer that I get, and it's wrong, this is what I get for not using numbers. I would have a spreadsheet, and I would sit here and plug it in until I got a right answer. In this case, it's 2.0 times 10 to the 8th ohms and negative, which means that the circuit really wouldn't work in order to achieve that time constant. Now, what would happen over the weekend is I'm going to sit with a spreadsheet and just plug in numbers until I get the right thing. So what you would do is you would find that RV using this procedure, and then the question would be, if the voltmeter was ideal, what is the new time constant? Now, because the new voltmeter is ideal, you can remove the voltmeter from the circuit, because an ideal voltmeter's resistance is infinite. If that's the case, REQ is equal to 1 over 200 times 10 to the 6th plus 1 over 400 times 10 to the 6th inverted. And that gives you .3 times 10 to the 8 ohms. Oh, I'm sorry, 1.33. And then the time constant, 1.33 times 10 to the 8th times the 10 times 10 to the negative 9. Gives you a time constant of 1.33 seconds. So the time constant changed from 4 seconds to 1.33. Now, for this, it's a little bit hesitant because the numbers really didn't work on the first one. But that's because I just pulled a number out of air. And because you guys love your numbers, I just need to make sure that I print or get the right one so that you don't get a nonsensical answer during the final. Yes, question. Or someone had a question. Yes.
Can we work that one that you said everyone got wrong where you have to find the potential at the point?
The potential at the point?
What was it? Or the voltage? It was on this.
Oh, okay. We'll do that one in particular.
Okay, for the circuit.
Yeah. So in this particular circuit, we have 8 resistors. All of them are 1/7 of an ohm, which seems pretty odd. The voltage is 1 volt. The first thing that you have to do is find the equivalent resistance. The first thing that I do for my boxes is I will collapse these two, and these two, because they are in series and you simply add. So this becomes 1/7, 2/7, 2/7, 2/7, and 1/7. Now I have 2 sets of parallel resistors. So my box will look like this. And that will collapse them down to 2/7 inverted plus 1/7 inverted, and you invert the whole thing. So 3.5 plus 7 and invert it, and you do mathy, and it's 2/21 for that. For this one, it is 2/7 inverted, 1/7 inverted, 2/7 inverted, and you invert that. So it's 14 inverted.
Why are you inverting everything twice?
Because when you do, hold on. The true definition of parallel resistors is 1 over Req equals 1 over R1 plus 1 over R2. So R1 and R2 you take the inverse of. The extra, the second inverse, comes from the fact that you need to determine what the equivalent resistance is. So you invert after you sum the inverted resistances. And that's where the second inversion comes from. Now I'm left with 2 circuits which are in series, 221 and 1 over 14. Now I just add. And then I have 1/6 of an ohm. Let me make sure I did this right. 2/7. Oh, 3.5 plus 7. Okay. So it's 1/6 of an ohm. Because my potential is 1 volt, so 1 divided by 1/6, I get a current of 6 amps. I was playing a lot of games with fractions. Now to get to VA. And to do that, what I'm going to do is look at that particular section. So all of these resistors are 1/7. Notice that when I first, or the last step before I calculated the total resistance, this block could be simplified by a 221 ohm resistor. That these two are equivalent. If it's 6 amps through here, it's 6 amps through the equivalent resistor, which means that the potential at the lower end is 1 volt minus, or actually we'll start with the top voltage minus the current and the equivalent resistance of that left-hand side. So this becomes 1 minus 6 times 221. Three-sevenths of a volt. That's the voltage at the lower end. Now that I have the high and the low, I can determine the resistance across this lower current. You could do it one of two ways. I'm going to do it this way. I know V high, I know V low, and I know the resistance in the middle. So this current here, I'll call that IB. Is 1 minus 3/7 divided by 1/7. So that will leave me with 4 amps on the lower end. If the total is 6 and the one going through the bottom is 4, then the one going through the upper one is 2 amps. Now that you know the current passing through the arc on the top, you can calculate the potential at this particular point, which we will call A. The voltage at A is 1 volt, the voltage at the high point, minus 2 amps times 1/7 ohm, which means that this is 1 minus 2 divided by 7, 5/7 of a volt. And that would be the potential at that particular point. I would use decimal, or 714 volt. And that's how you would do it. It's like a Sudoku puzzle. You gotta, It really tests the patience of a student because a lot of times they just want to go, bam, there's the answer. In this particular case, you really have to work 3 or 4 problems before you get to the one that you need to do. A lot of students really have difficulty with that. Yes?
Why do you use 2 over 21 for R plus?
Why did I use 2 over 21?
Yes.
That is, this 2 over 21 is the equivalent resistance of these 3 resistors. You can I was faced with a problem. I don't know what the potential is right there. However, all of this stuff here can be simplified into a 221 ohm resistor with 6 amps going through it. A voltage here with this is difficult to solve. This is a simplification, trivial to solve. So now with this, I can determine the potential at that point because the potential there and the potential there are the same. Once I have that, I can figure out the current going through this. Once I determine the current going through that, I can determine the current going through this, and then from there, I can determine the potential at A. It's a lot like, it's a Sudoku puzzle where there are literally 5 or 6 equations like this in here. And what you're looking for is points where you know 3 of the 4. And if you can identify 3 of the 4, you found that potential. Yes?
Why did you not initially just solve for the current in the upper loop?
You can.
It seems like an extra step.
Yeah, but an extra math step. What you can do, and you suggested it, if you know that point and you know that point and you know the total resistance, high, low, and here you do 2/7, you'd end up with 2 amps. Either one is fine. Depending on the situation, some people like to start at the bottom and work up. But this is kind of problematic. And actually, there's a third way that you can figure it out. You can figure out R equivalent for that guy and get the potential there rather than going from top down. So there's a lot of different ways that you can do this. But the key step is knowing this and wisely applying it. So, yes?
You asked on here, after we've done that, is it going up or down? How do you determine?
What do you mean?
Oh wait, never mind, that's the wrong. Never mind,
Okay.
that's Kershaw, sorry.
Okay. Yeah, the biggest mistake that this class did in that first test was only about a quarter got that right. So I would put that high on the list. That's why Kirchhoff's law is not as important. Okay, next question? Yes?
If we have questions about our test, can we ask you now or do it like?
Later, or after, once we break up.
Okay, yeah.
Okay, any other questions? Yes?
We did compound lens.
Compound lens, okay. And your question?
When did you do the second problem from the last test?
From test 3? Okay. Do you have a copy of test 3?
I did.
Which one? Number 2?
Yeah, that's in film.
Oh, thin film? Okay. Let me hold on just a second. Okay. What we're going to do is problem 3 from the final. It is not to scale. The object is 35 centimeters to the left of the convex. The concave is 33 centimeters to the right of the concave is right to the convex. Where is the image with respect to the convex lens? Total magnification, and describe the final image. So image 1 is 41.56 centimeters to the right of the convex. The first magnification I'm going to keep this in fraction. 35 is negative 19 sixteenths. That's the first magnification. The and this one is 41.5625 centimeters. Exact. Image 2 is focal length 2 inverted minus object 2 inverted, and then you invert that. Because image 1 is 41.5625 and the concave lens is 33, object 2 is 41.5625 minus 33. So the and it's got to be negative because it's to the right of the concave. So this becomes 41.5625 minus 33. Mathy. Negative 137 sixteenths. So the focal length is 1 over negative 17 minus 1 over minus 137 16. Let's clean this up just a bit. Negative 1 over 17 plus 16 over 137. And really, it's coming out to be image 2 is 17.25. And it is a positive 17.25. Which means that the image is real. Which means that the image is not only to the right of the concave, it is way right to the convex. So to reposition position the where it is 50.25 centimeters right of convex. Now what we need to do is find M2. M2 is minus I2 over O2, or minus 17.25 divided by minus 8.56, and this will give us 2.02.
Where did the 8.56 come from?
8.56 is 137 over 16. Now, we don't use the 2.02 to describe the final image. What we do use is M1 times M2. Might as well convert all of this into negative 1.19 times 2.02 will give me minus 2.40. So the image is real. The image is to the right of the concave. It is way right to the convex. It is inverted. It is enlarged. And that is the compound lens problem.
Wait, the image is real, you said?
Yes.
Wait, why is it real?
The final image is real because it has a positive image distance, which means that the image is to the right of the concave. If that final image distance was negative, that would mean that the final image was between the lenses, which means it's definitely virtual. For an image in a compound lens to be real, it has to be to the right of both lenses. Okay. Now your question. The thin film we have an even reflection that is constructive. It is similar, an even constructive is the same as an odd destructive, which means that 2t m lambda, and we get this equation m1 lambda 1 over n, because we have to consider the n of the glass, and 2t m2 lambda 2 over n for the other wavelength. Now the thicknesses are equal because you're using the same thin film. So m1 lambda 1 over n is equal to m2 lambda 2 over n. The n's cancel. Rearranging this, I get m1 is m2 lambda 2 over lambda 1. And what I'm going to do to solve for this a little bit more quickly is I'm going to take lambda 2, which is 400, and divide by 600, which gives me 2m2 over 3 is m1. This gives me the easiest way of just kind of eyeballing it and seeing what works out. If m2 is 1, m1 is 2/3. If m2 is 2, M2 is 4/3. If M3 is 3, then M2 is 2. So those are the values that you get. The thickness, now this was a common mistake by a few students. To calculate the thickness, you still need N. So thickness is M1 lambda 1 over N. You could use the other set and still get the same answer. So 1,000 nanometers. And so that's the thickness problem.
Will you be given the N value?
I will either ask for you to solve for it or I'll give it to you.
Where did you get the M3 equals 3? Was that given to you?
No, what you have to do is you have to systematically poke in numbers until you get 2 integers. And there were some people who discovered that M1 or M2 was 0. That will never work because you can't have a infinitely thin layer. Therefore, it's not a film. And so that's it.
If you can, when you're going through those numbers and you see 400 and 600, can you just go ahead and eliminate 1 and 2 because you know they're going to be fractions? Like,
Yeah, I mean, if you could sit there and in your head, I would
just show it. Like that. Oh, I tested 1. Oh, I tested 2.
I probably wouldn't. I'd probably just chase to the end. I don't think something like that. In some cases, it is kind of a miracle moment to just do that. But you could just say, plugging in numbers, I know for a fact that it's got to be 2 and 3.
Right. So like when you're looking at it, you know that.
Yeah.
3 times.
I was looking at this and going, yeah, this is it. So I wouldn't be looking for you to just write out like a list, and I wouldn't worry about that. Okay. Yes.
Did you leave out the 2 on the bottom? Because isn't it like 2t equals m lambda? So then you have to divide by 2.
Well, remember what I did is I said 2t is equal to 2t. So
I'm talking about on this other part.
on the other one?
Yeah.
Oh, I forgot the 2. Then it's 5.
Is it 500?
Yeah, it's 500.
Is that the red test?
What test do you have? It's red.
It's 500.
All right. So it's 218, so we're kind of at the end. Once again, it's going to be a straightforward test. Nothing, just completely right field. Yes?
The multiple choice, someone said that you said that it was going to be pulled from multiple choice in the semester.
Most will.
So, look, for this semester multiple choice and probably like summer.
Yeah, I'd go through the 214 from the summer and spring, which you have all the versions.
Are the old files on drop or on your Google Drive?
No, they're on Blackboard. Okay. Going once? Going twice?
You don't have to announce it for the last session.
Okay. Thank you, and I'll see you at the final.